So we are in Unit 3, Day 4, and we are going to learn about, among other things, the second derivative test. So we'll start with concave up and concave down. We'll discuss points of inflection, and then we're going to use the second derivative test to find relative extrema. So I'm going to draw two pictures. They're both going to look like parabolas. I can't draw straight lines today. There we go. All right. And the first one is going to just be simply a parabola facing upward somewhere. And the second one is going to have a parabola facing downward. Oh, there's a nice pretty one. I want this one to be pretty too. Oh, wrong way. Okay, so let's talk about the second derivative. And the second derivative is the derivative of y prime. So it is the rate of change of the rate of change. How fast is the rate of change changing? And what is it doing? So let's have a look. In this graph, we've got a negative slope, a less negative slope, a less negative slope, a slope of 0, a positive slope, and a more positive slope. So just making up numbers, this one might be -10, and this one might be -6, and this one might be -1, and obviously at the bottom we're 0. And then I could have a slope of 2, and then 5, and then maybe 9. And so this is a graph, and I should have said this first, this is a graph of y prime, right? So let's look at what's happening to our slope. This is not the graph of the function, this is a graph of y prime. It's going from -10 to -6 to -1 to 0 to 2 to 5 to 9. It is always increasing, right? So my rate of change is always positive. It's +4 here, it's +5 here, it's +1 here, it's +2 there, it's +3, and it's +4. So the rate of change of the rate of change, f double prime of x, is greater than 0. So we can see that when it's greater than 0, it's concave up. And our other one's going to be exactly the opposite. Positive, less positive, 0, negative, more negative. -8, -3, 0, +1, +7. Totally made up numbers, but it doesn't matter, you get the idea. It's always negative on the left, and it's always positive on the right.
Delilah's in the waiting room.
So if we look at this one, my slope, again, this is y prime. So let's look at the slope of the slope, right? It's going from -8. Sorry, wrong direction. These guys are positive, aren't they? +8, +3, -1. Those slopes are negative, -7. That makes a lot more sense. Okay, so I'm going from positive 8 to what? Positive 3 to 0 to negative 1 to negative 7. And if we look at that, I have lost 5. My rate of change is negative 3. The rate of change is negative 1. It's negative 6. It's always negative, right? So my f double prime of x is less than 0 will always give us this shape, which is concave down. Okay, so when I look at the slopes and I look at y prime, I can look at their rate of change and I can say, okay, the rate of change, what is it doing? So when I look at the graph, it's concave up. I look at the red, it's the slope, the first derivative. It is decreasing and then increasing. And then I look at the rate of change of that. I can see that when f double prime of x is greater than 0, it's concave up. And when it's less than 0, it's concave down. Okay, so let's have a look at what that does. When a curve changes concavity, that is called a point of inflection, also known as an inflection point. Okay.
You wrote infection.
Well, it's probably not good. An inflection point. Okay, so if I have a graph and I'm concave up, and then all of a sudden I turn and I'm concave down. That point where the graph changes, concavity, is called a point of inflection. What could also happen is when the first derivative is undefined, a curve like this, and in the middle, if my first derivative is undefined, it's quite likely that the second derivative is going to be undefined as well. Okay? So now that we've seen what happens, let's see if we can look at a problem and describe the concavity on the open interval. I'll leave that up for a second. Example 1, find the open interval of concavity. 4, f of x, or y, equals x to the 4th minus 4x cubed. Okay, the first thing we're going to do is find the first derivative. 4x cubed minus 12x squared. We do not need that, but we could use it for increasing and decreasing. But we do need to use the second derivative, so we need the first derivative to get there. 12x squared minus 24x. And so we set that equal to 0. I'm going to factor, and I get my possible inflection points, or pips. So my possible points of inflection are my possible inflection points. And now I'm going to do the same thing that I did yesterday with the first derivative, but I'm going to do it with the second derivative. So I'm going to make that number line, and I'm going to pick some points. -1 will be good, +1 will be good, 3 will be good. I'm going to look at f double prime of x. So when I look at f double prime of x, what happens to my sign? Let's see. Where are we? Down here. So f double prime of -1 is 12 times -1 times -3. That is a positive number. You don't need to actually show that. When I plug in 1, I get 12 times -1. That's negative. And when I plug in 3, I get 12 times 3 times 1, which is positive. So when it is positive, we are concave up. So I know my graph is doing this. When I am negative, my graph is concave down. I know I'm doing that. And when I am positive again over here at 2, I am concave up. Let's move this line. It's easier than moving the graph. All right, so here we go. So possible inflection point, concavity changed based on our signs. So we have identified the inflection points and we have found the intervals of concavity. So just like yesterday, we need the what, we need the where, we need the why. We are concave up on negative infinity to 0 and 2 to infinity because f double prime of x is greater than 0. What, where, and why? We are concave down on 0 to 2 because f double prime of x is less than 0. And we have points of inflection at x equals 0, doesn't matter, but I like the order, and x equals 2 because f double prime of x changes signs. You could write them individually, x equals 0 because it switches from positive to negative, and x equals 2 because it switches from negative to positive. All right, so all three have a what, all three have a where, and all three have the justification, which is the why. Okay, so that is our first example of using the second derivative, and we have found concavity. We have not seen the second derivative test yet. So the second derivative test is when f is a continuous function, let f be a continuous function such that f prime of x equals 0. This is the second derivative test, and we're going to look at the points, the critical numbers, where the first derivative is equal to 0. Here is where we find critical numbers and relative extrema, right? All right, so when that happens, what do we have going on here? We get a horizontal tangent line, which means that we have turned around possibly. So what we're going to do is we are going to look at the second derivative at these points. If f double prime of x is less than 0, how should I write this? I'm going to write the y first. It is a relative maximum. The reason why is because if f double prime of x is less than 0, I am concave down, and therefore at that point I will have a maximum because it is concave down. The second derivative tells me I'm concave down. If I'm concave down, I have a relative max. If f double prime of x is greater than 0, I have a relative min. And again, that's because when I have f double prime greater than 0, I have concave up. And if I have concave up, it's going to be a minimum. And finally, if f double prime of x is equal to 0, the test fails. Go use the first derivative test. So to emphasize, the second derivative test takes the critical numbers from the first derivative and plugs them into the second derivative. We do that, and we can have a look, and we can see what is going on at those points with concavity. And once we do, that'll tell us cup up, cup down, min or max. Okay, so let's discuss everything we've done so far to this point. If I take the first derivative, I get critical numbers, I get increase, decrease, and that is when I am positive versus negative. Second derivative, I get possible inflection points. I get concave up versus concave down, positive, negative. Okay, the first derivative test is for relative extrema, as is the second derivative test. And the first derivative test, we look at f prime of x, and if the sign changes, it's a min or a max, right? And I'll put relative in there. Doesn't tell us anything about absolutes. Second derivative test, find f prime of x equal to 0. Those are my critical numbers. Evaluate in f double prime of x. Put these into here. If I am positive, I am cup up, which is a relative minimum. And if I'm negative, I'm cup down, which is a relative maximum. All right, so that is a quick summary of the difference between first derivative and second derivative, and the first derivative versus the first derivative test, the second derivative and the second derivative test. Okay, let's put it all into play. Find the intervals of concavity. First derivative. F prime of x equals 3x squared minus 12x plus 12. Set that equal to 0. Find critical numbers, increasing, decreasing, but we don't care about that in this problem. Take the second derivative, 6x minus 12, and set it equal to 0. 6x equals 12, x equals 2. This is a possible inflection point. Put those numbers, which happens to be just 1, on a number line. Test those numbers. Negative nothing, 0, and positive 3. And if we look and we plug in 0, we get a negative. We plug in 3, we get a positive. So I have concave down on negative infinity to 2 because the second derivative is less than 0. And I have concave up on 2 to infinity because f double prime of x is greater than 0. It doesn't ask, but I have a point of inflection at 2 because I shift from up to down. All right. Find the relative extrema using the second derivative test. I know I went through the first one quickly, but we've already done that one earlier in the notes. Second derivative test of the same function, x cubed minus 6x squared minus 12x. first derivative, which is 3x squared minus 12x minus 12, which is 3 times x squared minus 4x, it's plus 12, plus 12, but it's factored out, so plus 4, which is 3 times x minus 2, x minus 2, which means that x equals 2, I have first derivative critical numbers. That's part 1. Part 2, find the second derivative. F double prime of x, the derivative of the derivative, we did it earlier, 6x minus 12. Evaluate my point in the second derivative. F double prime of x equals 6 times 2 minus 12, which equals 0. Test fails. But I don't stop there. Since the test fails, I go and use the first derivative test. So let's go back to the first derivative. Let's make ourselves a number line. Let's put our number 2 on there. Let's look at f prime of x, which is 3x squared minus 12x plus 12. And let's plug in 0, and let's plug in 3. And I'm going to use the factored form, which is 3x minus 2 squared. Think about that carefully. You can't get a negative number there. Plug in 0, negative 2 squared, positive times 3, positive. Plug in 3, you get a positive. And my increasing and decreasing didn't change either. So that means that I do not have a max or a min. There is no relative max. There is no relative min. So let's see what's going on here. We're concave up at up till 2. We're concave down after 2. But our function is always increasing. Let's see what this function looks like in Desmos. It looks like, I had it up earlier, x cubed minus 6x squared plus 12. X. Look at that. So, if I can get a point, and I trace, I am concave up to 2. Concave down, sorry. I'm concave up after 2. And you can see that my derivative is always positive, except at this 1.2, where it is 0. My concavity changes, so x equals 2 is simply a point of inflection. Now, I guess we knew that from concavity here, right? But the second derivative test for relative extrema failed. The first derivative test told us this increasing and decreasing, the slopes were always positive, which leads us to that final conclusion through the tests that the only thing it could be is a point of inflection. All right, we'll call this one E3. Find relative extrema. Using second derivative test of y equals negative 3x to the 5th plus 5x cubed. Second derivative test. First thing I have to do is find critical numbers, find the first derivative. Hopefully we did that. Negative 15x to the 4th plus 15x squared equal to 0. Negative 15 x squared can factor out. X squared minus 1, x equals 0, x equals 1, x equals negative 1, critical numbers. And all of these, of course, should be set equal to undefineds, but since there's no denominators, nothing can be undefined, right? All right, so now that we've got our critical numbers, step 2, find the second derivative. And my second derivative is what? Negative 60 x cubed plus 30 x squared. And that will give me negative 30 x squared times x minus 1 times 2 x minus 1. Hang on.
Isn't it just plus 30x?
Yeah, it's just x. So it's going to be, factor the x out, and it's going to be 2x squared minus 1. Okay, you don't have to factor it, but it's going to be a lot easier to determine what's going on. So we're going to look at f double prime of 0, f double prime of 1, f double prime of negative 1. When I plug in 0, I am going to get a negative number. No, I'm going to get 0. 0 times a negative, right? Which is 0. When I plug in 1, I'm going to get a negative times a positive. No, what happens when I plug in 1? Yeah, times a positive. And that is going to be less than 0. And at negative 1, I'm going to get a positive times a positive, which is greater than 0. Okay. At 0, my test fails. At 1, I am less than 0, so I'm concave down, and therefore I have a relative max. And at negative 1, I'm cup up, so therefore I have a relative min. I'm only going to write one of them, but we should do it for both. So we would then say x equals 1. Let's do it in a different color. X equals 1 is a relative max because f double prime of x is less than 0. I'll do both. X equals negative 1 is a relative min because f double prime of x is greater than 0. I always draw the pictures to remind myself, because usually when it's less than, it's the bottom, but it's opposite because it's concavity, right? So just draw a picture if you need to, or if you just memorize it, that's fine too. That's the second derivative test, everybody. If I look at my points, my xy points, when I look at the change, each one is 1, I gained 4. That's my rate of change, right? I gained 3, I gained 2, I gained 1. This tells me that f prime of x is greater than 0, and my function is increasing. When I look at the rate of change of the rate of change, right? It's going down, right? My rate of change is decreasing, right? It's going from 4 to 3 to 2 to 1. This is f double prime of x. F double prime of x is less than 0. I'm concave down. It's quite easy to plot these points. It's not as easy to plot them accurately on here, but we'll try it. All right, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At -4, I'm at 0. At -3, I'm at 4. At -2, I'm at 7. At -1, I'm at 9. And at 0, I'm at 10. So I'm going to put this other point a little bit higher. Now, because these points are so close together, it almost looks like it's linear, but it's clearly not. And you can see that we're increasing and that we're concave down. Find concavity on 6 over x squared plus 3. Now, to find my first derivative, I think I'm going to go 6x squared plus 3 to the -1. F prime of x then is -6 x squared plus 3 to the -2, which is -6 over x squared plus 3 squared. All right, I could try product rule. Wait, do I?
Don't you need to multiply by the derivative?
Yeah, I
inside
forgot
of
to
terms?
change. I'm like, I knew I forgot something, times 2x. And so we have 12x. And now I could end up turning it into a product rule with a -2. It gets pretty complicated pretty quickly. You can try it if you want. What I'm going to do is I am going to, see, I forgot the chain rule. I tell you guys all the time when I did it. Anyway, sorry. Here we go. Second derivative is a quotient rule. Lodi high, x squared plus 3 squared times -12 minus -12 times 2 x squared plus 3 to the first chain rule times 2x all over x squared plus 3 squared squared, so to the fourth.
For what you're subtracting in the numerator,
I am going to get -12 x squared plus 3 squared plus 24 times 2, 48 x squared times x squared plus 3 all over x squared plus 3 squared. So algebra 2 skills, factor out an x squared plus 3. And so I'm going to have an x squared plus 3, and I'm going to have left -12 times x squared plus 3 plus 48 x squared. And that is all going to be over x squared plus 3 to the fourth. This guy will cancel that down to a third. And if I distribute that -12, I will have -12x squared plus 36, -36, plus 48x squared all over x squared plus 3 cubed. So let's see what happens. 48 minus 12 is 36. X squared minus 36 over x squared plus 3 cubed. F double prime of x is then equal to 36 times x squared minus 1 over x squared plus 3 cubed. All right, so where do we get zeros? At plus or minus 1. So x equals +1 and -1 are my possible inflection points. That's a rather complicated problem. And honestly, the AP probably won't give you one that hard. We might. But this is a good problem. You might see something like this on a test. But the AP, they won't ask you to do concavity with something this hard. They'll ask you to do just the derivative or second derivative. All right, so now let's look at concavity here. We're going to look at -1. We're going to look at +1. We're going to look at -2. Let's look at 0, and let's look at +2. When I plug in -2 on the top, I will get a positive number. When I plug in -2 on the bottom, I will also get a positive number. So I am positive. When I plug in 0 on the top, I will get a negative. When I plug in 0 on the bottom, I will get a positive. And when I plug in 2 on the top, I get a positive, and 2 on the bottom, I get a positive. And so there's my concavity, and this is f double prime of x. So what does that tell us? I'm not going to do all the writing. This is cup up, this is cup down, and this is cup up. And you would have to write it and explain it and justify it just like we did on our other problems. All right. However, we'll end it there.